Hello. The purpose of this very brief video is to work out for you rotational dynamics using the work energy theorem and energy conservation. I'm just going to give you two examples, work it out in detail. I have done this in my class lectures. This is a bit of a slower lowdown on it, just to help you work out problems. So let's get started. Let us take a pulley like this and draw this out. Okay, so, and then what we do is we attach a string to this pulley. And let's say we apply a force F. And because we have applied this force F, the string is going to come down, right? Sorry, come down like that. And let us assume that the distance by which the string, the distance by which the string comes down, this distance is y, okay? So we can assume a certain mass for this pulley, and let's say the radius is r. So the moment of inertia I, for a disk now, because the pulley is usually approximated with the disk, is found to be 1/2 m times r squared. So what are we doing? Our goal is to study rotational dynamics. And first we'll study rotational dynamics using work energy theorem, which turns out to be a very useful tool for figuring out, for example, something like how the wheel is turning faster and faster as this string here is going down because of the application of a force. I could have attached a mass here maybe, but I've chosen not to. I'll do it later, so that way you'll be able to see how that is being done. So clearly, if I apply a force across this height y here, the work done by the force is W, and this W is equal to F times Y, because both F is downward and Y is downward. They're parallel, so the cosine of the angle between two parallel forces here would be 0. So F times Y times cosine of 0. Cosine of 0 is 1, so it is F times Y. So at this point, we are going to use, as I said, work energy theorem. So therefore, F times Y is going to be equal to change in kinetic energy of the wheel or of the pulley or disk, as you want to call it. So initially, before this force was being applied, let's say the omega I was 0, was not turning. And then there was a final omega F. And the question we can ask is, what is this final omega F? So from work energy theorem, we know then that the change in kinetic energy will simply be 1/2 I omega final squared. So let's be a little careful here. You are talking energy from rotation of a rigid body. This is your rigid body here. And the equivalent of kinetic energy, the equivalent of mass in rotating solid objects is moment of inertia. So this is moment of inertia. And then you have the angular velocity or speed, which is omega. And here we are talking about omega final. only because omega initial is 0. So what we therefore have is Fy is equal to 1/2 omega final square. So now it is very, very simple to find omega final. It is going to be twice Fy divided by I. And since I is 1/2 mr square, I already told you that, it's right here. So you have twice Fy times 1/2 mr square. This thing, of course, should be raised to the power of half. This also should be raised to the power of half. Observe that this too shows up as a division of a division. So therefore, you'll have 4Fy times mr square raised to the power of half. So this therefore gives you the omega final for the rotating wheel. If you want to figure out what the velocity of the tip of the string is, you can also calculate that by simply doing the final velocity for the tip of the string. Let's say there's a very tiny mass attached to it. Let's say we are ignoring the value of that mass. It's very tiny. So then V final is going to be omega final times R. So you can also find the V final, which would be the velocity right here at this point, let's say B. Okay. And this point can then be regarded as A. We are going to do this problem in a slightly different way, but instead of doing it with work energy theorem, I will do it with energy conservation. So let's do this problem with energy conservation. It's the very same problem, so I'll quickly draw it. Then you have a wheel here. Okay. And then you have, let's say, a string, and you attach a mass here. Call this mass small m. This mass is big M. The radius here is R. Let's call this point A. And let's call the ground level B. This is point B. Let us say the mass starts at A and comes down to B. Let's call this height H. Okay. So since we are going to use energy conservation, we have to use the equations associated with energy conservation. So we are doing rotational dynamics with conservation of energy. Okay. So now what we do is we first write down the total energy at A. Let's call this EA. And so EA would be small m GH, because this is the situation where small m is here. But do not forget to add the potential energy of the pulley itself, which would be big M G times H. And now correspondingly, you can forget about what happens in between, but you can try to compute the total energy at B. Now at B, mind you, this mass is coming down, it's moving down, so it's speeding up. So there should be some kind of a V final here. And this V final obviously will be related to omega final associated with how fast the wheel is turning. And like before, we again assume omega initial to be 0, which means that at A there was absolutely no motion, which we have already implicitly assumed because there is no kinetic energy term in EA. So now the total energy at B is going to be EB. And EB is going to be 1/2 M times V final square. So that's no biggie. Of course, you still have the pulley itself hanging up there. So that's MGH. But now the pulley is turning. So then you need a 1/2 I omega final kinetic energy of the pulley. because of its rotation. So if you let energy be conserved, so EA be equal to EB, then let's write it out. So we have mgh plus big mgh is equal to half m v final square plus big mgh plus 1/2 I omega final square. So let's get rid of this big mgh that shows up in both places. We don't need it here. So we are left with the slightly simplified equation here, but you have to further simplify it because, first of all, the moment of inertia I is 1/2 big M times R squared. Big M, of course, is the mass of the pulley out here. And omega final and V final are related. So we can write V final is R times omega final. And this, of course, is something that we connected to no slipping condition. So a no slipping condition, just to go over it very quickly, incorporates three statements. First is that displacement x is R times turn of the angle theta. V is R omega, and A is R alpha. So we are just using this one here, okay? So what does no slipping condition mean? So once again, it means that as the string unwinds and the pulley turns, the way the string comes down and the amount by which the pulley turns, they are related by these three conditions. And any one of them typically ends up being useful. So in this case, because you have omega f, clearly you want to connect omega and V, and because V is here, and therefore you pull out this one. That's simply what you're doing. So therefore you can write mgh equal to 1/2 m V final square plus 1/2 times 1/2 mr square times V final square over R square, because that's what this term here is. So the R square happily goes away. And so you have mgh is equal to 1/2 m V final square plus 1/4 big M V final square, which can be simplified 1/2 V final square small m plus 1/2 big M, such that this 1/2 and this 1/2 makes this 1/4. So we are almost done. So we can then write V final as 2m GH divided by small m plus 1/2 times big M. And this, of course, is going to have to be square rooted. So now you see, you have found V final. And if you want, you can also find omega final, because we already know from here that V final is R times omega final. So V final divided by R is going to give me omega final. So in other words, this expression here incorporates not only how fast this mass is moving as it's about to get to B, it also tells us how fast this wheel is turning as the mass is about to hit B, because of no slipping condition, the downward motion of the mass and the anti-clockwise turn of the wheel are perfectly linked by this no slipping condition equation. All right, thank you.